Our last video ended with the visual areas of our brain, so how we receive information and how we interpret that information. So today we are going to move on to the auditory areas. So we have a primary auditory cortex, which is going to be in the superior margin of our temporal lobe, which makes sense because auditory information comes in from our brain and gets interpreted in that temporal lobe. The auditory association area is located just behind that, and it stores memories of sounds, permits perception of a sound stimulus. I'm sure each of you, there's a sound that you hear and you automatically connect it to some kind of a memory, whether that's good or bad. So I know for a lot of us, that's the sound of the alarm going off in the morning. Our vestibular cortex is going to be the posterior part of the insula, so remember deep inside, and it's going to be adjacent to the parietal cortex. So this is going to be responsible for our conscious awareness of balance, so position of your head in space. If you've ever had a head cold or had an ear infection or had really a lot of fluid behind your ears, you'll notice that your balance is off, or it makes that really difficult. Or different substances can also affect our vestibular cortex and affect our balance. Our olfactory cortex, or the primary smell center of our brain, is also a really interesting part. So this is going to be on the medial aspect of our temporal lobe. So part of our rhinencephalon. So when you see the root word, let me show you this. When you see the root word rhine here, think of like a rhinoplasty or a nose surgery. So rhine is always going to mean nose for us. So here the rhinencephalon literally means nose brain. So how your brain is able to interpret information coming from our olfactory bulbs and tracts, or how we interpret smell. So whatever is left over from this. So mostly in us right now, it's just the ability to smell things, but the remainder of the rhinencephalon is part of our limbic system, the limbic system controlling our emotions. So it explains how we have conscious awareness of odors, or how a certain odor can still evoke strong emotions. Now that could be something good, like the smell of fresh baking bread reminds you of your mom making bread on a Saturday morning. It's a warm, comforting memory. Or if you've ever left something in the refrigerator too long, like a bag of spinach, and then you take it out and you open it, that is not a good memory. But we always have those memories attached to odors because of a rhinencephalon. There we go. Okay. So our gustatory complex is also in the insula, deep to the temporal lobe. That's involved in our perception of taste. Our visceral sensory area, so remember viscera, the term viscera meaning our guts, internal organs. So this is going to be posterior to that gustatory cortex, and it's going to be involved in perception of visceral sensations. So if you've ever eaten so much that your stomach feels stretched and super uncomfortable, or the same thing with your bladder, that is where we get that feeling, that sensation that, hey, this is uncomfortable, I don't like this. So if we look at those areas on our brain, we can see vision here. Our primary visual cortex is this really small area, but the visual association area, or where those things are interpreted, surrounds that. Now they're not clear-cut areas, obviously. Our primary auditory complex is here, kind of where our ear hole would be, right in there. We also have our auditory association area, so what interprets those sounds. And then we have Wernicke's area. So this is a highly specialized area of our brain, similar to Broca's area. So this is going to be part of our posterior association area, and we'll talk about that in just a little bit and how highly specialized it is. Taste, balance, all of those things are going to be found in our temporal lobe as well. So damage to our primary visual cortex results in functional blindness. So that small, dark blue area, if something happens there or that gets damaged, that is functional blindness. Now, anyone who has damage to the visual association area surrounding that cortex, they're still able to see, but they can't comprehend and interpret what they're looking at. Strange stuff. Okay, so our multimodal association area receives input from different sensory areas, and it's going to send output to multiple areas as well. This allows us to give meaning to the information that we have received, store it in our memory, and tie it to a previous experience and decide on actions. So I think a great example our book gives us is if you ever in chemistry class, let's say you're working with acids and bases, you accidentally drop a beaker of acid. Probably a little bit of panic initially, but you remember the smashing of the glass, you feel the acid splatter on your leg, there's that oh crap moment, what do I do? And then you decide on your action. So you're going to go to the washing station, pull that lever, and hose yourself off. So what that means for us is we've got all of this different visual input, whether it's taste, sensation, what the area of the room looked like at the time. So that next time we go into chemistry class, you're going to be uber careful about how you handle your acids from then on out. This area is associated with sensations, thoughts, emotions, things that make us who we are, those experiences that we have. So it's broadly divided into three parts. We have our anterior association area, the posterior association area, and the limbic association area. And remember, we talked about the limbic system being involved with emotions. So our anterior association area is also called our prefrontal cortex. It's the most complicated cortical region of our brain. It's involved with our intellect, our cognition, recall, your personality, like all the things that make you you. So this contains working memory needed for abstract ideas, judgment, higher reasoning, persistence, and planning. So these things develop depending on the feedback that we get from our social environment. So when you are younger, your judgment, your reasoning, your planning are not necessarily higher order functions or things that come naturally. They're things that we gain by experience, and we get better at the older we get, hopefully. Our posterior association area is a large region in our temporal, parietal, and occipital lobes. It plays a role in recognizing patterns and faces and orienting us in space so we know where our body is. It's also involved in understanding written and spoken language. So that Wernicke's area that we talked about, there's a condition called aphasia, and it has to do with our speech. So people who have Wernicke's aphasia aren't able to understand written and spoken language, which sounds really interesting. Other types of aphasia might be you put in words into a sentence where they don't belong, just as an example. And we'll talk about aphasia a little bit later on too. So our limbic association area is part of the limbic system. It provides emotional impact that makes a scene important to us and helps us establish those memories. So I'm sure you can all think of, something that has happened that has deeply affected you emotionally, whether it's something good, winning a state championship or being voted MVP, or a death, something, that's negatively associated with those feelings, or a song that's associated with an emotion that helps us set a scene and kind of keep and establish those memories. Okay, so interestingly, tumors or other lesions on our anterior association area can cause mental and personality disorders, including, loss of judgment, attentiveness, having zero inhibitions or not caring what people think. An affected individual can be completely oblivious to social norms. Perhaps they don't really care about how they appear. Maybe they engage in riskier behavior. My fourth grade teacher, I'll never forget, her name was Mrs. O'Neill. She was a wonderful, kind, sweet woman. You'd ask anybody and that's what they would have nothing negative to say about her. Probably about, I think when I was in high school, her personality really kind of changed on a dime. She became, really angry, really combative. She was just kind of hostile. She really wasn't herself. And they tried everything they could to figure out what was wrong with her. Her hormones were checked, her blood glucose levels were checked. It wasn't until they did a CT scan and found a tumor on her anterior association of her brain that kind of explained why she went through this really drastic, personality change. Okay. Different problems arise for people with lesions in the posterior association area. They give us awareness of ourself in space, where we are. What's really kind of crazy about this is individuals who have an injury to the posterior association area may refuse to wash or dress the side of the body that's opposite or contralateral to the lesion. So if they have a lesion on the right side, they don't think that that left side, that left limb belongs to them. It is not mine. This is not part of my body. So really strange phenomenon that can happen. Okay. So this probably is one of the more interesting parts of this chapter that I really like. And it talks about our cortical functioning and our lateralization. So how we divide work between our left and right hemispheres. So we know that we use both hemispheres for almost every activity, but these hemispheres are not equal in terms of functioning and what they do. They're not identical. Our cerebral dominance means what hemisphere is dominant for language. So it's not necessarily the same for everybody. And 90% of the people, humans have a left-sided dominance. So greater control over language, ability, and math logic from the left side of our brain. Consequently, because we know things work opposite, usually these people tend to be right-handed. In the other 10% of people, these roles of the hemispheres are going to be reversed. But some people, some lefties who have a cerebral cortex that functions bilaterally are what we call ambidextrous. I know we've had conversations in class about this before. I tend to write left-handed, but I do a lot of things with my right hand. Sometimes I'll go to grab a pair of scissors and I'll put it in my left hand like I'm going to cut something, and it doesn't feel right. And I'm like, I don't use my left hand like for scissors, so I put it in my right hand. But sometimes those things get screwed up, and it just has to do with how our brain communicates between our left and right hemispheres. So again, in this 10% of people, they're typically left-handed. What's really interesting is that they tend to be more free-spirited, more involved in visual spatial skills, intuition, emotion. They're more artistic and have just a general propensity for musical skills. They tend to be poetic, very creative, and insightful. So those aha moments, those, light bulb goes off, they come to those people a lot faster. I shouldn't say faster, a lot more naturally, I should say. Okay, so cut that section off. So when we talk about our cerebral white matter, so this is the second of those three basic regions of our cerebral hemisphere. So these are going to be responsible for communication between cerebral areas, between our cortex and the lower central nervous system. So this is going to consist of myelinated fibers that are bundled into these very large tracts. So we know myelin means it is going to send information very quickly. It's got enough cushioning and lubrication to push those messages really fast. So classified according to the direction which they run. So we have these association tracts, commissural tracts, and projection fibers. So in your brain, this is generally what they look like. Now, sadly, we don't have these cool neon pink and purple and blue tracks, but they're highlighted here to show you the direction that they run. And then here's what they're actually going to look like in our brain. So our corpus callosum is going to be part that connects our two hemispheres. So we have these anterior association fibers, or the pink fibers here. They're going to run the same way in our brain here. We also have green commissural fibers that are going to run east-west, and there's an area for those as well. So you can see also we have really, really long tracts that are going to run all the way down into our brainstem and spinal cord. Zoom that out. Okay. So again, these association fibers, they are going to run horizontal and are going to affect different parts of the same hemisphere. So they're going to stay either in the left or in the right. We have commissural fibers that are horizontal fibers, again, that are going to connect to the two hemispheres. So they're going to run in between, not just sticking to left or right. The largest commissural fiber that we have is called our corpus callosum that connects the two hemispheres. So you can actually have developmental issues with your corpus callosum, so it could not fuse. So meaning our left and our right sides are not able to communicate at certain areas. And then finally we have projection fibers. So what's different about these is they run vertically and they connect our hemispheres with the lower brain, so the spinal cord. So instead of running left to right, these are going to run north-south. So these are going to be sensory. It allows sensory information to reach the cerebral cortex, and then it makes a motor output through those same projection fibers. So if we look at them laterally, so we can see the association fibers here are going to stay in the same hemisphere. Our commissural fibers, these green guys, are going to run in between the two, but again, they're horizontally and are going to connect the left and the right hemispheres. And then finally, we have our projection fiber. So you can see all of that information is coming down here into the brainstem. So sensory information coming in, integration, motor output coming out this way. And finally, the third of the three basic regions of the cerebrum. We're almost there, hang on. Each hemisphere has a basal nuclei that is going to contain a caudate nucleus, putamen, and the globus pallidus, okay? So the only thing that you need to know of all of those is going to be the striatum. That is going to be the most important part. I don't necessarily need you to memorize what is going to go into that striatum. Okay, so if we look at that guy, it looks very similar to our ventricles, right? Okay, so the function of our basal nuclei are thought, or we say thought, to influence our muscle movements, play a role in cognition and emotion, regulate the intensity of slow or stereotyped movements. So here what we mean is an example would be your arms swinging while you're walking. So if you've ever, I think a really good example of how this information kind of gets crisscrossed would be if you've ever watched, and I hate to single the freshmen out, or younger kids do jumping jacks, and we know that our arms and our legs are kind of moving the same, but if you've ever watched somebody that looks like they can't do a jumping jack, like it just doesn't look right, they're not able to put those like slower stereotyped movements together, this would be a really good example of how that eventually becomes a learned pattern. It also helps us to filter out incorrect or inappropriate responses, or to inhibit antagonistic or unnecessary movements. So it helps us make smooth and coordinated and controlled movements, and helps to push out any of the stuff that we don't need. So with practice, something becomes smooth and coordinated. Parkinson's disease, Huntington's disease are both disorders of the basal nuclei, and I know that you've seen examples of both of those. And we've come to the end. So that is the end of section 12.2, and we'll pick up with 12.3 later.